Greetings everyone, my name is Waladit Deo Nathatkun and today I will present my final report for the finite element method course. My topic is finite element analysis of car rear spoiler under aerodynamic downforce. In this presentation, I will explain the motivation for the study, the modeling approach, the finite element setup, the results, and the conclusions and future improvements. So first, let's begin with the motivation behind this study. Rear spoilers are not only for appearance. In automotive design, they are used to improve aerodynamic performance, especially at high speed. A spoiler works by generating downforce, which pushes the car closer to the road. This increases the tire grip, improves cornering, and helps braking stability. So even though the spoiler looks simple, it plays an important role in vehicle performance. However, the spoiler itself must also be strong enough to carry the aerodynamic load acting on it. As vehicle speed increases, aerodynamic force increases very quickly, so the spoiler can experience significant pressure. This is why finite element analysis is useful. It allows us to estimate stress and deformation before manufacturing a real part. That helps improve safety and reduce design costs and time. The main problem in this project is that a spoiler must generate downforce without failing structurally. One concern is excessive deformation. If the spoiler bends too much, its shape changes, and that can reduce its aerodynamic effectiveness. Another concern is stress concentration. The load on the wing is transferred through the brackets and base plates, which are much smaller areas. Because of that, those regions are more likely to experience high stress. So the goal of this project is to check whether a simplified spoiler design can safely withstand aerodynamic loading without excessive deformation or exceeding the material use strength. To study this, I use ANSYS mechanical APDL and following this clear workflow shown to the right of the presentation slide. First, I created the geometry of the spoiler assembly using solid block volumes. Second, I defined the material properties. Third, I tested three element types, solid 185, solid 186, and solid 187. Fourth, I applied the boundary conditions and loading. Finally, I ran a static structural analysis and compared the results. A mesh convergence study was also performed to make sure the results were stable and not too dependent on mesh size. Several assumptions were made to simplify the model. So first, the problem was treated as a static structural analysis, so the aerodynamic load was assumed to be constant. Second, the material was assumed to behave as linear elastic, which means it's returned to its original shape after the load is removed, as long as the stress stays below yield. Third, the real spoiler shape was simplified into a block-based model. This makes the analysis easier while still keeping the main load part of the structure. The analysis used the Newton millimeter megapascal unit system for consistency. And finally, all parts were assumed to be perfectly bonded so that they behave as one body. The selected material was aluminum alloy 606-T6. This material is commonly used in automotive and aerospace applications because it offers a good balance of strength, low weight, and corrosion resistance. The key properties used were first Young modulus, which is around 69,000 megapascal, Poisson's ratio, which is at 0.33, and yield strength, which is equal to 276 megapascal. Young's modulus represents stiffness, while yield strength tells us the stress level where permanent deformation begins. Later, I used this yield strength to evaluate the factor of safety. The spoiler model consists of three main parts. So the first is the wing. The wing has a span of 1000 millimeter and a chord length of 220 millimeter and a thickness of 20 millimeter. This is the main load carrying surface. It is supported by two brackets, each with a height of 120 millimeter and a width of 20 millimeter. At the bottom, the base plates measure 120 mm by 80 mm and represent the mounting interface to the vehicle's body. Although simplified, this geometry still captures the main structural behavior of a real spoiler. To simulate the spoiler attached to a car, I applied fixed supports at the bottom surfaces of both base plates. This prevents movement in all directions. For the aerodynamic load, I use the dynamic pressure equation, which is Q equals zero point 0.5 times rho times V squared, where Q is the dynamic pressure, rho is the density of air, and V is the velocity of the airflow. Because velocity is square, this means that if the vehicle speed doubles, the aerodynamic pressure becomes 4 times larger. This is why aerodynamic load become increasingly important at high speeds. For this study, I use a pressure of 1,200 Pascal or 0.0012 megapascal applied uniformly on the wing surface. Using the wing area of 220,000 square millimeters, uh, the total equivalent aerodynamic force can be calculated using F equal P times A, where F is the total force, P is the pressure, and A is the loaded area. This gives an equivalent downward force of about 264 Newton. So the first element tested was solid 185. This is an 8-node first-order solid element with 3 translational degree of freedom at each node. Its advantage is that it is computationally efficient. However, because it uses linear interpolation, it is less accurate for bending and curve deformation. That means it usually needs a finer mesh to achieve good results, especially in areas with stress concentration. The second element was solid 186. This is a 20-node higher order solid element that uses quadratic interpolation. In simple terms, it can represent curve deformation better than solid 185. The third element was solid 187, a 10-node higher order tetrahedral element. It also uses quadratic interpolation and is useful for complex shapes. In general, higher order elements can capture bending and stress variation more accurately, often with fewer elements. For all 3 setups, I use free tetrahedral mesh. This was chosen because the geometry is complex and includes intersections between the wings, brackets, and base plate. So a structured mesh would be more difficult to create here. I tested mesh sizes from 50 millimeter down to 2 millimeter. A finer meshes improves accuracy because it captures geometry and stress variation in more detail, but it also increases computation time. So a balance between accuracy and efficiency is needed. To check mesh independence, I perform a convergence study using maximum total displacement. This was chosen because displacement is the primary variable solved directly in finite element analysis and is usually more stable than stress. The results show that solid 185 was more sensitive to mesh size and needed a finer mesh before stabilizing. In contrast, solid 186 and solid 187 converge much earlier, showing that higher order element can provide accurate results with less mesh refinement. I did not use maximum stress as the main convergent measure because of stress singularities. These often occur near fixed supports or sharp corners. In those regions, the stress can keep increasing as the mesh becomes finer, as shown in the figure below, even though the overall solution is already stable. So for convergence, displacement is more reliable. Stress results are still important, but they must be interpreted carefully near supports and geometric discontinuities. Now let's talk about the result. So for setup 1, using solid 185 with the optimized 3 millimeter mesh, the maximum deformation was 0.0322 millimeter and the maximum one misses stress was 1.81 megapascal. The deformation contour shows the largest displacement at the free wingtips, which is expected because those are the farthest point from the supports. The pattern is symmetric, which confirms that the load and boundary conditions were applied correctly. For setup 2, using solid 186 with a 10 millimeter mesh, the maximum deformation was 0.0391 millimeter and the maximum bond misses stress was 1.76 megapascal. Even though the mesh was coarser, this higher order element captured the bending behavior more accurately. This shows that accuracy depends not only on mesh size, but also on the quality of the element formulation. For setup 3, using solid 187, the maximum deformation was 0.0392 millimeter, and the maximum stress was also about 1.76 megapascal. This result is almost identical to setup 2, which gives confidence that both higher order elements are capturing the structural response well. The highest stress appears near the connection between the wings, brackets, and base plates, which makes sense because these are the main load transfer regions. The maximum one Mr. stress is about 1.8 megapascal, while the material yield strength is 276 megapascal. So the factor of safety is calculated by dividing yield strength by maximum stress, which gives a value greater than 150. This is very high, but it is important to interpret it correctly. In this project, the analysis only considered a simplified static aerodynamic downforce of 264 Newton. In real life, a spoiler also experiences vibration, road shocks, braking, and acceleration forces, crosswinds, fatigue, and local stress effects around mounting points. So this factor of safety should be seen as the safety margin for the loading condition study here, not the full real-world safety factor of a production spoiler. The deformation results also support the conclusion because the maximum displacement is only about 0.039 millimeter, which is very small compared to the overall size of the spoiler. In conclusion, this project successfully performed a static structural finite element analysis of a rear spoiler. The mesh convergence study showed that higher order elements, especially solid 186 and 187, are more efficient than solid 185 because they achieve accurate results with less refinement. The analysis also showed that the spoiler design is structurally safe under the applied aerodynamic load with very small deformation and very low stress. For future work, the model could be improved by using a more realistic spoiler geometry, applying pressure from CFD instead of uniform loading, including bolt holes and contact conditions, and performing model analysis to study vibration and resonance. Thank you for your attention, and that's all for my presentation.